So in the last couple of chapters, we've seen how atoms work. We've looked at the building blocks of matter, of how we get different elements from atoms, and how the nuclear chemistry inside those atoms takes place. Now let's look at the other type of pure substance, and that is compounds. Now, there are two types of compounds we're going to look at. We're going to look at ionic compounds, and in chapter 6, we're going to look at covalent compounds. Okay, so we'll start off looking at how atoms themselves combine to form compounds, what drives this forward, and focus in this chapter especially on ionic bonding. So, as I pointed out, compounds are pure substances formed when atoms of different elements combine chemically. There's a chemical reaction, or we form chemical bonds between these atoms, and that creates a compound where you have more than one element making up your pure substance. Now, what are these chemical bonds? How do they work? And what causes them to happen in the first place? Okay. So, what really drives bonding forward is stability, right? Atoms of a particular element might not be stable on their own, and so they turn to chemical bonding as a way to become more stable. By combining with other atoms or atoms of other elements, they achieve some stability, and that's again why we have these chemical bonds, right? That pulls them together. It's a way that they obtain this stability. But what is the stability they're trying to get? To understand this, let's look at elements that don't require bonding. In other words, the noble gases. And if you remember back in chapter 3, when we first talked about the elements, I pointed out that the noble gases in group 18 are called noble because they are very stable. They don't like to bond with other elements. They like to stay by themselves because they're pretty much happy the way they are. Now, what is the reason for this? If we look at their electronic configurations, you'll notice that their outermost shell is complete. So their s and p orbitals are full, right? So their electron configuration always ends with something s2, something p6. Okay, and we call that a noble gas electronic configuration. So when atoms engage in chemical bonding, as we'll see in this chapter and the next chapter, they're trying to get this stable configuration. They're trying to also have 8 valence electrons in their outermost shell. Okay? Now, this rule of 8 electrons is known as the octet rule. Okay? So, for example, if you look at a sodium atom, right, a sodium atom becomes stable by turning into a sodium ion. The way it does this is by losing its outermost electron, its valence electron. So out of its 11 electrons, it loses that 11th electron, and it leaves behind 10 electrons in total. Okay, this is the same electron configuration as neon, okay, which is a noble gas. So out of those 10 electrons, 2 of them are core electrons trapped in that 1s orbital. The remaining 8 electrons are those outermost electrons meeting the octet rule we were talking about. Okay. Now, how atoms go about meeting this octet rule depends on the type of atoms that are combining, the types of elements that are combining. I gave you an example just now with sodium. Metals in general will tend to engage in what we call ionic bonding. So you have metals that lose electrons, and they lose them or transfer them to nonmetals. And this transfer of electrons causes your metals and nonmetals to form charged ions, hence the name ionic bonding. These positive and negative ions then attract each other, because that's what positive and negative things do, and that's how we form ionic compounds. So for example, sodium chloride, your regular table salt, is an example of an ionic compound where your sodium forms sodium ions, which are positively charged, and they attract the chloride ions, which are negatively charged, which become chloride ions because they gain those electrons that the sodium lost. We'll go into more detail on how this happens in this chapter, so we'll come back to this idea in a slide or two. In the next chapter, we're going to look at covalent bonding. Now, covalent bonding is a type of bonding that exists between nonmetals alone. So, since nonmetals like to gain electrons to reach the octet rule, we'll reinforce this in a little bit. Um, Basically, covalent compounds come about because nonmetals will bond with each other by sharing their valence electrons rather than transferring them as we see in ionic bonding. Okay, so a covalent compound is when you have nonmetals sharing electrons. That's where the word covalent comes from. Covalent means sharing of valence electrons. So let's focus on ionic bonding and see how atoms meet the octet rule by forming ions. Okay, I gave you that example earlier with how sodium does it. Let's look at just metals in general, look at a few more examples there. Okay, so metals typically have only a few valence electrons. The example I gave earlier with sodium, sodium only has one valence electron, right? Its 3s1 electron is the only electron it has in that outermost third shell. Okay, so metals in general find it easier to meet the octet rule by losing these few valence electrons and dropping down to the previous noble gas. Now, electrons are negatively charged, so when a metal atom loses these negative electrons, what's left behind is a positive ion. It's positive because it still has the same number of positive protons despite losing its negative electrons. Okay, so that charge imbalance leaves behind a positive ion. So I give you an example there with sodium. So sodium, when it loses that one electron it needs to get down to the noble gas configuration of neon, it loses that one negative electron, and as a result, we're left behind with a positively charged sodium ion. Now notice that the name doesn't change. So we start off with a sodium atom. What we're left with on the right is a sodium ion. Okay, and the difference there, of course, is that now we represent that positive charge on our sodium with a little plus sign in the top right corner. Okay. You'll sometimes see people write down 1 plus instead of just plus. The 1 is kind of unnecessary. It's kind of like in algebra. You never write down 1x, you just write out x. It's kind of understood when you see that sign that there's one of it. Okay. The only time you need to put a number in front of that is if there's more than one. Okay. So here we have magnesium. Magnesium is in group 2. So it has 2 valence electrons, right? So out of its 12 electrons, 2 of those are in its outermost shell. Okay. So it loses those 2 valence electrons to drop down to the previous noble gas, which is the configuration of neon. Kind of similar to what your sodium did. But of course, with magnesium, it needs to lose 2 electrons to accomplish this. So when it loses those 2 electrons, you wind up having a 2 plus charge on your magnesium. Okay, so again, we represent that by writing a 2 plus in that top right corner. So magnesium goes from being a magnesium atom to being a magnesium ion. Okay, again, notice that the name doesn't change. It's still magnesium. It's just we acknowledge that now it's positively charged, and that's why we acknowledge it's an ion as opposed to a regular neutral atom. Here we have aluminium, right, or aluminum to use the American spelling and pronunciation. Aluminum, or aluminium, has 3 valence electrons. It has 13 electrons in total, but 10 of those are in innermost shells. 3 of them are in its outermost shell. So you go from being an aluminium atom to an aluminium ion. Okay? And so to do that, you've got to lose those 3 outermost electrons, and the resulting ion has a 3 plus charge. Okay? So typically speaking, with the main group elements, you can kind of look at their location, what group they're in, and use that to determine the charge. So group 1 metals will tend to lose 1 electron. Group 2 metals, like calcium here, will lose 2 electrons, because that's the number of valence electrons they have, and that's why they're in group 2. And they'll therefore form 2 plus ions. Okay? The calcium becomes a calcium ion with its 2 plus charge. So just to summarize all of our metals, all of our group 1 metals will lose their 1 valence electron to form +1 ions to be like the previous noble gas. All of our group 2 metals will lose 2 electrons. That's the number of valence electrons they have, and that's why they form 2+ ions. And then aluminium being group 3 metal will lose 3 electrons to form its +3 ion. Okay. Other than these, zinc and silver are two other metals that do form fixed ions. So if you want to remember them, and if you look at your periodic table, you'll see that aluminium, zinc, and silver are kind of diagonally related to each other. Okay, so if you look at their location in your periodic table, you'll see that aluminium's over here in group 13 or 3A, depending on your periodic table. Then you have zinc, getting into the transition metals, and of course silver is also a transition metal. So you'll notice that aluminium forms 3+ ions, zinc forms 2+ ions, and silver forms +1 ion. And you kind of have to memorize that, unfortunately. We'll see that for the other transition metals, things get a little bit more complicated, and you need a little bit extra information to solve problems involving them. But as far as zinc and silver go, as transition metals, those charges are pretty much set. Okay, and so you have to know that. Okay, the generic term for a positive ion is a cation. Okay, so just if you ever hear the term cation, just realize it's talking about a positive ion. Okay, what about nonmetals? Nonmetals typically have several valence electrons. That's why they're towards the right of your periodic table. So these atoms find it easier to meet the octet rule by gaining electrons. It just makes more sense from an energy standpoint. It's easier to gain electrons to become like the next noble gas. You only have to gain a few electrons to do that. As opposed to losing all of those many valence electrons to drop down to the previous noble gas. That's a lot of electrons you've got to pluck off for a non-metal. Okay, so you can't treat nonmetals the way you treat your metals, which only have a few valence electrons. So how does this work? Well, again, you're still meeting the octet rule. You're still looking at your number of valence electrons for your nonmetal. But now you're looking at how many electrons do I need to add to get to 8 valence electrons to match the next noble gas. Okay, so for example here, let's look at fluorine. Fluorine is in group 7A, or 17 if you have a newer periodic table. And it wants to be like the noble gases, which are one column to the right of it. So fluorine has 7 valence electrons. It needs to gain 1 electron to have 8 valence electrons and become like the next noble gas, neon. Okay, and so when it gains that 1 negative electron, it winds up having a negative charge. Okay, so that negative electron, that extra negative electron, gives it a negative charge. Just like our other ions, we represent that charge in the top right corner. Now, the difference here when it comes to naming these nonmetal ions, these negative ions, is that the name does change in the ion form. So fluorine is the name of our atom here that's neutral, but when it gets turned into an ion, we take that first syllable, fluor, and we add an "ide" suffix to the end of it. So it becomes a fluoride ion. Okay, so fluorine is a neutral F atom. Fluoride is F minus, so fluorine with a negative charge. Okay, so like this, like fluorine, we can look at the group any of our nonmetals are in and immediately figure out what their charge is going to be when they form ions. Bromine, which is also in group 17, will, just like fluorine, form a -1 ion. And just like fluorine, its name's going to change. Instead of bromine, we take that first syllable, brom, and we add that "ide" ending to it. It becomes bromide. So this is a bromide ion here on the right, okay, with a -1 charge. Okay, and again, please note that they each form a -1 charge, because they're in group 17 and they need only one electron to become like the next noble gas. Let's look at something in a different group. Oxygen is in group 16. Okay, so it needs 2 electrons to become like the next noble gas. And in doing so, it picks up a 2 minus charge. Notice that here, because we have more than one charge, we have to put a number saying how many there are. So this is a 2 minus charge. So we start off with oxygen. That's an oxygen atom on the left. That's neutral. Now we've got to take that first syllable, ox, and add our ide ending to it. So on the right here, we have oxide, which is oxygen with a 2 minus charge. Okay? And again, you can determine that charge by figuring out that oxygen is in group 16 and therefore needs 2 electrons to become like a group 18 noble gas. Okay, so here's sulfur. Okay, sulfur being group 16 will also form 2 minus ions. What's the name of this sulfur ion? Take that first syllable, sulf, and add ide to it. It's sulfide. Okay. So again, the group your nonmetal is in will tell you the charge of the ion it will form. So your group 17 nonmetals will have a -1 charge, your group 16 nonmetals will have a 2 minus charge, and your group 15 nonmetals will have a 3 minus charge. Again, notice that we're stopping at phosphorus and sulfur. Once you start getting lower down the periodic table, you go through the metalloids and into the p block metals. You go across that sort of staircase border that divides your p block. So please keep in mind that those elements below that border are metals, and so they don't form negative ions. It's only the nonmetals that are to the top right of your periodic table that do that. Okay? All right. Quick note here about that generic term for referring to negative ions. We call a negatively charged ion an anion. Okay, so these are all examples of anions. If you ever get confused between cations and anions, the way I tell students to remember it is a cation is positive, and it's kind of hard to see this in me showing you a PowerPoint. I do this live, but when I say the word cation, I make a kind of just an action, drawing kind of imaginary whiskers with my fingers near my face, and for the word positive, I kind of turn my hands into like kind of claws. Sounds probably really weird when I'm trying to describe this verbally, but basically, picture a cat, and cats have paws. Okay, so that's one way to remember that. So yes, the cations are positive. Okay, anywho, moving on. So we see that our metals form positive ions, right, our cations, and our nonmetals form negative ions. Well, how do these come together to form ionic compounds? Positive and negative ions attract each other. Just opposite charges attract each other, and it's this attraction that gives us a lot of those physical properties that we see in ionic compounds. Okay, so basically we get this huge network of these positive and negative ions attracting each other, and we call this network a crystal lattice. Okay, a lattice. It's spelled Lattice. I believe I have it on the next slide. And I'll show you a picture of what this looks like. Now, because we have so many of these ions together, that's what, that this cumulative positive negative attraction winds up being a very strong effect. This is why we often see that ionic compounds tend to have very high melting points. So here's a picture of our crystal lattice. Okay, so this is an example with sodium chloride, and you can see how our sodium ions and our chloride ions pack together to maximize the positive-negative interaction, that positive-negative attraction between our cations and anions. So notice that by packing together this way, you're surrounding each ion by ions of the opposite charge. So for example, if I look at, let's say, this sodium ion over here, look at how many chlorides are surrounding it. You can see 1, 2, 3, 4. There's a fifth one behind it. that's kind of obscured there. And if this crystal structure were to continue, there'd be a sixth one placed in front of it here. Okay. Likewise, any chloride ion is surrounded by 6 sodium ions as well. So if you look at this chloride over here, it's got 1, 2, 3, 4 sodium ions. There's a fifth one behind it that's obscured and you can't really see. And a sixth one would be placed in front of it here if we were to continue this lattice. Okay, so given the large number of interactions there, that's why the cumulative effect is that these ions are held together very tightly, very strongly. It takes a lot of energy to overcome these attractive forces, and that's why ionic compounds tend to have very high melting points. So, if we have this huge network, this crystal lattice where you have, millions, billions, trillions, really like numbers larger than that, we'll look at the scale of these numbers in a couple of chapters. But we're talking about lots and lots and lots of ions being held together in these crystal lattices. How do we represent a chemical formula summing up that interaction, summing up the relationship between these the metals and nonmetals? Well, to write out a formula, we use the simplest ratio between those ions. Okay, so to do that, we look at the charge on each of the ions and ask ourselves, how many do we need of each of our ions to balance out the positive and negatives and get a net charge of 0? Okay, so how many cations, positive cations, do we need, and how many negative anions do we need to have the positives and negatives cancel each other out? Once we answer that question, we represent those numbers by using subscripts. A subscript is a number that's written a little bit lower, smaller and lower to your symbols for your elements. Okay, so they're written to the bottom right of the element's symbol that they belong to. So let's see a couple of examples and see how that works. So let's say we're looking at sodium chloride. A sodium atom has one valence electron, so it loses that one electron to form a sodium ion with a +1 charge. As you can see here, it does that by transferring that one electron to a chlorine atom. Chlorine needs only one electron to meet the octet rule, so it takes that one electron and forms a chloride ion with a -1 charge. Now, +1 and -1 are equal and opposite charges, so they actually balance out to give you that net of 0. Right? +1 - 1 equals 0. So you only need one sodium ion and one chloride ion to balance out those charges. So when we write out the formula of sodium chloride, we just have one of each element. Okay, now, so technically there's a subscript here of 1. We don't bother writing it though. Just like I mentioned with charges, and kind of like how we do with x in algebra, it's kind of silly to write the 1 in front of something because it's understood that there's one of it when you see it there, right? So you don't bother writing 1x, you just say x, right, in algebra. In the same way, like, if you have a +1 charge, you just say plus, right? If you have a -1 charge, you just say minus. You don't have to say 1 minus or 1 plus. So likewise, we don't bother putting a subscript of 1 here because it's understood that there's one sodium and one chloride by not writing any numbers. Okay, let's see an example where we do have to put subscripts. So let's look at magnesium chloride. Now, magnesium, unlike sodium, has 2 valence electrons. It loses both those valence electrons to meet the octet rule, and it forms a 2+ ion in that process. Now, in order to do that, it's got to give both those electrons away. So if we're pairing it up with chlorine to make chloride ions, each chlorine can only accept one of those 2 electrons. So you need 2 chlorines to take both those electrons. Okay. Alternatively, you could explain it by the fact that we have each chloride with its -1 charge. Well, we need chlorides to balance out the 2 positive charges on our magnesium ion. So if we have 2 positives, we need 2 negatives to balance that out. So how do we write out that formula? Well, again, there's only one magnesium here, so we don't bother putting a subscript. But to show that there are 2 chlorides, we put a 2 as a subscript next to the chlorine, okay, in the chemical formula. Again, notice we're using just the symbols for those elements that we saw way back in chapter 3. Okay, so in our chemical formula representing the compound here, we have we write it out as MgCl, or as MgCl2, sorry. So let's try another one here. Here's sodium and nitrogen combining to form a sodium nitride. Now again, you can see that sodium's in group 1, so it forms ions with a +1 charge. Nitrogen is in group 15. It has 5 valence electrons, so it needs to pick up 3 more to become like a noble gas. So when it does so, it gets a 3- charge. So it needs 3 sodium ions to balance out that sodium, that 3- charge on our nitride ion. And therefore the formula is Na3N. So notice we put the 3 after the sodium to show that there are 3 of those sodium ions for every one of our nitride ion. Everyone please notice that even though these ions are charged, when we write out the formula, we don't write down the charges. Okay, we drop the charges there to kind of show that they're balanced out. Okay, the only time you ever want to write out your charges next to your atom is whenever you're showing an individual ion, just to distinguish it from a neutral atom. Okay, whereas here in a compound, it's kind of understood that they must be charged if they're bonded together like this. Okay, so we don't bother writing the charges there. Okay, so far at all of the examples we've looked at, the charges on our ions have been easy enough to figure out using our periodic table. With our metals, we can figure out the charge based on the group that the metal is in. If it's in group 1, it'll form ions with a +1 charge. If it's in group 2, it'll form an ion with a 2+ charge. Likewise, with our nonmetals, we can figure out their negative charge by working backwards from how many columns away from the noble gases they are. So group 17 is -1, group 16 is -2, group 15 is -3, and so on. It gets a little bit more complicated when we deal with transition metals. Transition metals, with the exception of zinc and silver, basically have the ability to form more than one type of cation. And that's really just a neat property of transition metals and yields a whole bunch of interesting chemistry that you can do with them as a result. But it makes things a little bit confusing when it comes to naming them. So to get around this, we have a special system for naming these multiple cation metals. Okay, we call this the stock system, and I'll get into it in a couple of slides. But first, let's practice naming these single cation metals, the group 1 and group 2 metals, or aluminium, zinc, and silver compounds. Okay. So when it comes to naming these compounds, I don't know if you noticed when I was verbally saying the names of the formulas we wrote out earlier, but you typically just say the name of the ions involved, right? So, for example, if you have a sodium ion and a chloride ion coming together, you just say, well, this is called sodium chloride. Likewise, if you have magnesium ions and chloride ions combining, you just call it magnesium chloride. Notice, by the way, that we don't make a reference to how many ions there are when we're saying the name of the compound. So even though there are 2 chlorides for every 1 magnesium ion in magnesium chloride, we just say magnesium chloride. We don't reference the 2 anywhere in the name. Okay, so it's pretty straightforward. You just say the name of the metal, and of course the non-metal, your anion, has to have that "ide" ending. Okay, so you just say the name of your metal plus the name of the root of that non-metal plus that "ide" ending. Okay, and you have a space in between the two. Okay, there are 2 words that make up this name. Let's try a couple of practice problems here just to get the hang of this. So here we have NaI. Okay, so Na is sodium. Okay, and again, if you aren't familiar with all the names of these elements, I recommend having a little table out with a list of the more common elements, or just have some way of looking it up for now. But eventually you'll hopefully start getting, need to rely on that table less and less as you start getting familiar with more of the names. especially some of the more common names like sodium and potassium and so on. Oxygen, sulfur, chlorine, bromine, fluorine, etc. Okay, so Na is sodium. Over here, this is an L. This is an I, not an L, right? Does everyone see that? You have to have two elements making up your compound, right? If it was one element, it would be a pure, it would be an element, not a compound. Since elements have to have a maximum of two letters here, this third letter must be a capital letter belonging to a new element. So that's a capital I, not a lowercase l, just so everyone's aware. Okay. So Na is sodium. Okay. And capital I references iodine. Okay. So let's write out the name for this compound. So sodium stays sodium. Your positive ion, which is always listed first in your ionic compound, keeps the name of the metal it comes from. So a sodium ion is just, we just call it sodium. Its name doesn't change from sodium. Iodine, on the other hand, being your negative ion, listed second, has to change its name to have that "ide" ending. So you take that first syllable, well, kind of a syllable and a half of iodine, we take iod, and add "ide" to the ending of it. So it becomes sodium iodide. That's the name of our compound here. Okay? So let's try a second one together. Here we have Ca, that's calcium. F stands for fluorine, but remember, we want to take that name, we take that first syllable, fluor, and we want to add that "ide" ending to it. So it becomes calcium fluoride. Again, please note that that 2 over there does not show up in the name anywhere. It's just calcium fluoride. It's understood that you need 2 fluorides to balance out with calcium, because calcium being in group 2 has a 2 plus charge, fluorine, or fluoride rather, being in group 17 has a -1 charge, so you're going to need 2 of them to balance out the 2 positives on your calcium ion. Okay? So you don't need to reference that in the name, because that's the only formula calcium fluoride can have. There's no other way to combine calcium and fluorine to make calcium fluoride. Okay, so I'm going to move on from here, but feel free to pause this video and try out these other practice problems, and then I will, feel free to press play after that, and the answers will hopefully be up. Okay, so here are the answers to all these practice problems. Feel free to try them out on your own time. Quick note here, Ag is silver, and again, even though silver is a transition metal, silver and zinc are those transition metals that have fixed charges. So notice that we just call this silver chloride, because AgCl is the only combination of a silver ion with a chloride ion. So, what do we do for the other metals, the transition metals, besides silver and zinc, that can form more than one ion? Okay, remember, this is an interesting property of our transition metals. For example, iron comes in 2 forms. It can come in a +2 form or a +3 form. Okay, so you can have an iron 2+ ion or an iron 3+ ion. Okay, which again yields some really interesting chemistry. I think back in chapter 3, I talked about how we're able to breathe, we're able to absorb oxygen from the air because of iron's ability to do this. So the iron in the hemoglobin in our blood is in this +2 form. When it absorbs oxygen from the air, it's able to do so because it changes to this +3 form. Okay. But the problem here then is that we can't use our periodic table to remember this, right? These numbers don't match up with the location of iron in the periodic table. And so unlike your group 1 and group 2 elements, you can't tie those together. So we need extra information in the name of our compounds to figure out what type of iron we're dealing with. So to do this, we use what's called the stock system. The stock system uses a Roman numeral in parentheses to show you what the charge is on your ion. Okay, so for example, we would call this iron 2 using a Roman numeral 2, and we would call this iron 3 with the Roman numeral 3 to represent that 3 plus charge. So, when you write out your name of an ionic compound that happens to have a transition metal, the rules are still the same as for the other ionic compounds. You still say the name of your metal, you still say the name of your non-metal with its "ide" ending. The only difference is when you write out the name of your metal, you should add in its charge in Roman numerals. Okay. So let's see an example of how we can figure that out. Let's say we have the formula Cu2O. Now, Cu is copper, okay, and O is oxygen. So if this were a regular simple ionic compound, we would just call this copper oxide, right? Because Cu is copper and O is oxygen. We take that first syllable ox and we change it to that oxide form. Okay, so oxide is the anion name for an oxygen ion. However, copper is not in group 1 or group 2. It's one of those transition metals, and you need to put a Roman numeral after it because it is there's more than one type of copper out there. And we want to specifically refer to the copper that is in that's in Cu2O over here. Okay? So, how do we figure out the Roman numeral that belongs to this version of copper? To do this, we actually have to work backwards. Our periodic table doesn't tell us this, but our periodic table does tell us what the charge is on our oxide ion, right? Because oxygen is in group 16, or 6A, so it must have a -2 charge, again, because it's 2 groups away from the noble gases. So if your oxide ion has a 2- charge, what must be the charge on your copper ion to give you this formula here? Okay, so if you want to see how this works, basically, a good way to set this up is to kind of divide your formula in half. So you start off with our formula, Cu2O. We don't know what the positive charge on our copper is yet. That's what we're trying to find out. But we do know that this is a -2 charge on our oxygen. So to help understand this, I'm just going to divide my formula in half here. Okay, so I've got the metal half of my formula and the non-metal half here. And we know that for a formula to work properly, these charges have to balance out. We saw that earlier with our other ionic compounds, that there must be a net charge of 0, where our positives and negatives cancel out. So first ask yourself, how many negative charges do we have? We have only one oxygen here. There was no subscript, but that means that basically it's a subscript of 1. So -2 times 1 is -2. And so in order for this to balance out, our coppers must have a +2 charge, so that -2 and +2 cancel each other out. So what must the positive charge on each copper be if 2 of them gives us a +2 charge? Well, +2 divided by 2 is +1. So we know that this must have a +1 charge. And so we show that by using the Roman numeral 1 in our name for copper. So instead of just saying copper, we call this copper 1, where we put 1 in our in parentheses, our Roman numeral 1 in our parentheses. And of course, the oxygen becomes an oxide ion, as we've seen already, and so we just combine this to make our name. It becomes copper 1 oxide. Okay, so please note, we don't just call it copper oxide. That would be incorrect, because that doesn't give us enough information about the copper. So we need to know that the copper in this type of copper oxide has a +1 charge, and that's why it's copper 1 oxide. Let's practice this a few more times. Okay, so here we have Fe(I3). Okay, Fe is iron, which again is a transition metal that's going to need a Roman numeral. So let's work this out and see what must the charge on our iron ion be if it requires 3 of these iodides to balance it out. Okay, so first of all, Fe is iron, okay, and I is iodine, so we know it's going to form an iodide ion. What's the charge on an iodide ion? So look at your periodic table and you'll see that iodine is in group 17, so an iodide ion will have a -1 charge. Okay, remember, it's one group away from your noble gases. So if you have 3 of these negatively charged iodide ions, what must be the charge on your lone iron ion to have those charges cancel out and give you a net charge of 0? So you can solve this accordingly and figure out that the iron must have a +3 charge, and therefore it's iron 3 iodide. If you're having trouble seeing it, because if you don't like manipulating algebraic equations like this, I can set it up the same way I set up the previous example with copper 1 oxide. So if we start off with Fe, again, we don't know the positive charge on it yet, we're going to figure that out, and we have it paired up with an iodide that's got a -1 charge. Well, -1 times 3 is -3, which means our irons must be +3 to get these charges to cancel out. So if there's only one iron, what's 3 divided by 1? Well, it's going to be 3, and that's why we get that Roman numeral of 3. Okay? So this has to be a 3 plus charge, and it's this number that gives us that Roman numeral over there. Okay? All right. Why don't you pause this video and try the next 2 examples? I especially like this second example over here, because notice that this is also a copper oxide. This is actually the other type of copper oxide, not the one that we just saw in the example in the previous slide. So pause this video, take a second and try these ones out, and then I'll put up the answers. You can see if you got them correct. Okay, so hopefully you've tried this out now. So we have CuO, and you've probably figured out that since your oxide has a -2 charge, your copper must have a +2 charge to balance it out. This is copper 2 oxide. Okay, and the next example over here, that's tin 2 bromide. Now, I want to draw your attention to something here, and that is where are these Roman numerals coming from? Because there's a common mistake that a lot of students make. A lot of students will look at that subscript 3 over here and say, oh, that's where that 3 comes from, because 3 iodides. I have a 3 in my formula. That must be included in my name somewhere. This is a coincidence, okay? It doesn't always have to be that way, and sometimes it isn't, and when it isn't, you're going to get that question wrong. You only need to look at the next example to see this in action. Look at CuO. There's not a 2 anywhere in this formula, and yet the formula is copper 2 oxide. So again, the reason for this is that it's a +2 charge on this copper. Okay, the copper must have a +2 charge to balance out with the 2- charge on our oxide, and it's this 2 plus charge that gives us that +2, or the Roman numeral 2 in our name. Okay? In the case of here, like your iron 3 iodide, again, it's the +3 charge in the iron that gave you that Roman numeral, not the subscript 3. Now, the subscript 3 comes about because you're going to need 3 of these -1 ions to balance out that +3 charge. So it's related, but it winds up, getting a little bit more complicated, or at least, you'll get a different answer when your anion doesn't have a -1 charge like it does here. Okay, so watch out for that. That's a common mistake students run into, so please don't make that mistake. All right, here's some more practice problems. Again, feel free to pause this video and try these out on your own time. Okay, but here are the answers if you want to check your work. Okay, so you've seen that basically when it comes to writing out names from formulas, we basically just write out the name of our cation and the name of our anion. In the case of our cation being a transition metal, we've got to do that extra step of figuring out its Roman numeral, but otherwise the rules are still the same. What about going from formulas, or getting names, or going from names to formulas, rather? Okay, so we've seen how to go from formulas to names. How did we go from names to formulas? Well, we've kind of already seen this a little bit. We saw earlier how we can balance out the charges on our ions to get the proper formula we need. So here, we need to figure out the ions we're dealing with first, based on our name, and then just balance them out as we saw earlier. Okay, now when it comes to things that don't have a Roman numeral, you can use your periodic table to figure out their charges. If you have a transition metal, the name will have a Roman numeral that'll tell you its charge. So again, you can use that to your advantage to help figure out the charges you're dealing with. So let's see some examples here. Lithium chloride. Okay, so notice that there's no Roman numeral in this name, so that tells you lithium is probably in group 1 or group 2. And sure enough, if you look it up in your periodic table, you'll see it near the top left. It's in group 1, which tells you that lithium has a +1 charge. So its symbol is Li and has a +1 charge. Chloride. Where does that root word chlor come from? Well, it comes from chlorine, which has the symbol Cl. And so if it's in group 17, it must have a -1 charge. So here are the ions we're dealing with. We have an La plus ion and a Cl minus ion. Now at this point, it's just like any of those earlier combinations we saw where we've got to figure out how many we need of each ion to balance out our formula. So in this case, +1 and -1 cancel each other out. So balancing this is going to be really easy. We just need one of each ion. And so our formula is just going to be LiCl. That's the formula of lithium chloride. Okay, let's try something where we have to do some balancing. So let's say we wanted to write out the formula of iron 3 oxide. Now, that Roman numeral there is going to be useful because it's telling you the charge on your iron. Okay, iron is a transition metal, so you can't use your periodic table to figure this out. The iron we're using in this problem has to have the charge of 3 plus because of that Roman numeral. So the symbol for iron, which you can get from your periodic table, is Fe, and so we write it as Fe with a 3 plus charge. Oxide, of course, comes from oxygen, which has the symbol O, and since it's in group 16, it has a -2 charge. Okay, now notice that these charges are different, so we've got to balance this out, and this takes a little bit of extra work. I think some of the examples we saw earlier where we were balancing charges were a little bit simpler, right? You just had, you had -1s or +1s, and so you just had to multiply by the number that you needed to balance out with. Here, we've got a 3 and a 2, so those don't balance out as simply. So we've got to figure out how to balance this. Now, there are two ways to do this. Okay, you could either use what I call the lowest common multiple method, which I personally prefer, or you could use the crossing method, which a lot of students prefer. It's a little simpler, but there's a common mistake that arises from it that you've got to watch out for. Okay, I'm going to show you both methods. Again, you want to pick the one that you probably find easier, and feel free to use it, just pick one of the methods. You don't have to know both methods. Okay, so if we have a +3 and a -2, what's the lowest common multiple of 3 and 2? Okay, because we need to work out how to balance out these positive and negative charges to get a net of 0. So the lowest common multiple, that's the lowest number that both of those numbers can be divided into while still giving you a whole number. Okay, the lowest common multiple there is 6. Okay, 3 times 2 is 6, and 2 times 3 is 6. Okay, those are whole numbers. So let's write out the formula. We need to figure out how many do we need of each ion to get to 6. So if we have, Fe3 plus, how many 3 pluses do we need to get to 6 plus? Well, we're going to need 2 of them. Okay, so for iron, that subscript's going to be 2, because we're going to need 2 of these irons to get 6 positive charges. Likewise, if we have oxides with a 2 minus charge, how many of these 2 minus charges are we going to have to combine to get to 6 minus? to get 6 negatives? Well, we're going to need 3 of these oxides, because 3 times 3 times 2 minus gives us 6 minus. So we're going to put a subscript of 3 next to our oxygen. Okay? So that's going to wind up being the formula, Fe2O3, and that's the lowest common multiple method. Asking yourself, what's the lowest common multiple of those two charges, and then how many do you need of each ion to get that lowest common multiple? Now, the crossing method simply takes the absolute value of your charges and just crosses them over. The 2 from your oxides, 2 minus, comes down here next to your iron, that you can see over here. The 3 from your 3 positive charges on your iron comes down next to your oxygen, your oxide, as you can see over here. Now, the problem with this method is, while it's simple, there's a common mistake that arises when you have numbers that can be simplified. Okay, so if you have to make sure that this ratio of subscripts is the simplest possible ratio. If they can be simplified further, you need to simplify it further. So let me give you an example of a problem where we run into that pitfall with the crossing method. So let's say we were trying to draw out the formula for chromium 6 oxide. Okay, so chromium 6 is Cr with a 6 plus charge, as that Roman numeral tells us. Oxide, of course, is still 2 minus. Now, if you try to do the crossing method, you'd say to yourself, all right, that 2 comes down here, that 6 comes down here, right? But there's a problem with this, right? Because 2 and 6 can be further simplified. If you wrote down the formula Cr2O6, this would actually be wrong. 2 and 6 are both divisible by 2. So 2 can be simplified to 1. 6 divided by 2 is 3. The formula of chromium 6 oxide is actually CrO3. Okay, and this would be the correct answer. If you wrote Cr2O6 by using just the crossing method without simplifying, you would actually get that problem wrong. It has to be the simplest ratio between your subscripts. Okay, so something to keep in mind there when you're doing problems like this. Okay, but that being said, of course, please pick whichever method you find easier, okay, and that you will consistently get correct. So whether it's the crossing method, where you're just keeping in mind that you've got to keep your simplest ratio, or the lowest common multiple method, the bottom line is you balance these charges and you wind up with the formula. Okay, so in this case with iron 3 oxide, we need 2 irons and 3 oxygens, or 3 oxides, for this to work, and that's why the formula is Fe2O3. Okay, that brings us then to polyatomic ions. Now, we have looked at all the ions we've used so far in our ionic compounds have been what we call monoatomic ions. These are ions made up of just one element. So our cations are made up of one metal, our anions are made up of one nonmetal. Okay, now we put subscripts to help balance out our equation, but the ions themselves have only a single metal or nonmetal. Polyatomic ions are interesting because they take multiple nonmetals that are covalently bonded together. We'll look at covalent bonding in the next chapter, of course, but for now understand that this is how we can clump together a bunch of nonmetals. But in the case of polyatomic ions, instead of being neutral molecules, they wind up happening to have a charge. And because they are charged ions, they can engage in ionic bonding, and that's the case here. We have to name these compounds that have these ions present, and we have to use slightly different rules because they are polyatomic ions, not the monoatomic ions that we have seen. Now, when I say that we use different rules, the rules for balance out the formulas, for coming up with names themselves, like for combining the names of our cations and anions, all those rules are still the same. You actually don't have to learn anything new as far as that's concerned. What's different is the names of the ions themselves. Instead of getting that nice "ide" ending, we tend to see a lot of examples with "ate" or "ite" as the suffix of our ions. Now, there are exceptions to this, of course, and I'll get into that. But those are the most common type of polyatomic ions you'll see. All right. So, so typically, the most common polyatomic ions you'll come across are what we call oxyions. These are nonmetals, things like like nitrogen or carbon or sulfur, phosphorus, combined with one or more oxygens, and these are typically negatively charged ions. So you'll see, for example, nitrate has a nitrogen combined with 3 oxygen atoms, and that whole thing has a -1 charge. Okay. Now, you'll notice that I call nitrate nitrate. It has that 8 ending. Likewise, there's nitrite out there, and I'll show you the relationship between those. But that's typical of a lot of these oxyions. You're going to see either 8 or ite endings, and that's, if you see that name ending with 8 or ite, that kind of gives you that hint that you're dealing with a polyatomic ion. There are a couple of exceptions to this in terms of the types of polyatomic ions you'll come across. The While an ide ending is typical of a nonmetal monoatomic ion, there are 2 polyatomic ions that end with ide. That is hydroxide and cyanide. Okay, so you may have to get comfortable with seeing those and recognizing that it's not a monoatomic, which hopefully should be relatively easy to do, because as soon as you look at that root word, you'll quickly find like there's no element that has the root word hydrox in it or cyan in it. So you can tell, hopefully, recognize those quickly as polyatomic ions. The other exception you may want to memorize is the ammonium ion. Ammonium is the only positively charged polyatomic ion you're going to come across. Okay, so it's 1 nitrogen combined with 4 hydrogens, and this whole thing has a +1 charge. Okay, so even though it has that IUM ending, it's technically not a metal, right? It's made up of nitrogen and hydrogen, which are nonmetals, but it behaves metallically because of this positive charge. So it is possible to get an ionic compound where that cation listed first is ammonium. Okay, so that being said, I recommend eventually getting to the point of memorizing some of the more common polyatomic ions. I will say for the quiz on this and maybe the exam after, don't stress. I don't expect you to fully memorize them immediately. So I will provide you with some help on those quizzes to help remember those polyatomic ions. But I think it is good for you to eventually memorize them, because it'll make doing problems involving polyatomic ions a lot easier, and it'll also help you avoid making mistakes, because you can recognize those polyatomic ions as being present and not mistake it for multiple anions of multiple monoatomics, which I think is a common mistake a lot of students make. Okay. Now, there are ways to memorize this that'll save you some brain space. There are memory devices that'll help you remember this. If you get a chance, Google the term Nick the Camel. Okay, so it's a memory device. So about a camel named Nick who ate a clam supper in Phoenix. I think it's something along those lines. There are different variations of that sentence where they add different words, but each of the words in that sentence, each of the nouns at least, reference a polyatomic ion. The first letter tells you the nonmetal that is present. So, for example, the name Nick is to help you remember the formula of a nitrate ion. So the capital N there gives you the N of your nitrate ion, that nitrogen. The number of consonants in the formula tells you the number of oxygens. So there's an N, a C, and a K in Nick. So that tells you there's 3 oxygens in our nitrate. The number of vowels, in this case there's only 1 vowel, that I, tells you the charge on your ion. So nitrate has a -1 charge. Okay? And so each of those words in that sentence will help you remember the polyatomic ion. So again, when you have time and you're trying to learn your polyatomic ions, that might be an avenue to explore to help you memorize it. I'm also going to get into the relationship between the eights and the ites. and especially if you scale that further up or down. So for example, the per-ites and per-eighths and the hypo-ites. We'll get into that in a couple of slides. There's a good crash course video that helps you, that goes over some of those nomenclature rules. So, I recommend watching that if you get a chance. By the way, a crash course has an entire chemistry playlist. So if you're not already familiar with them, please do check them out. Hank Green, like myself, tends to talk a little fast sometimes. So the nice thing about these videos is that you can always pause us when we start, talking a little too quickly. Okay, so the rule that helps you, if you can memorize all of your 8 endings, okay, so all of your 8 ions, you can accordingly figure out the formula of the corresponding ite ion. All you have to do is drop an oxygen, but make sure that the charge does not change. So for example, if you memorize that phosphate is PO4 with a 3- charge, well, phosphite is PO3 with a 3- charge. You just drop one of the oxygens, but make sure that the charge does not change. Likewise, sulfate is SO4 with a 2- charge. Well, sulfite, you drop an oxygen, so it becomes SO3 with a 2- charge. Okay, so notice that 4 drops down to a 3, so that charge doesn't change. Likewise, nitrate is NO3 with a -1 charge. Nitrite is NO2 with a -1 charge. So your 3 drops down to a 2 for your oxygens, but your charge of -1 stays -1. Now, please note there is no absolute rule that connects 8s with either number of oxygens or charges, right? So notice that phosphate has 4 oxygens, but nitrate has 3 oxygens. Okay? Notice that phosphate has a 3- charge, but sulfate has a 2- charge. So again, there's no relationship there between these names and the number of oxygens or the charges. You just have to memorize them. Okay, so my point here though is that if you can memorize all the 8 ending ones, you automatically have a way of knowing what the ite ending ones are. Okay, you just drop an oxygen accordingly. And so that saves you having to memorize both sets of names. Okay, and that makes your job a little bit easier. Now, I mentioned that you can extend beyond this simple 8-ite relationship. You can especially see this in the chlorate family. Chlorate is a polyatomic ion, which is ClO3 with a -1 charge. And there are similar ions that continue in that vein, just swapping out the halogen. So instead of chlorate, you could have bromate, where you have a bromine instead of the chlorine, and so on. So how do we extend beyond chlorate and chlorite? Well, chlorate, as I mentioned, is ClO3 with a -1 charge. Okay, so we have 3 oxygens, 1 chlorine, and that whole thing has a -1 charge. If we add oxygens to this, we would add a per prefix to it. So perchlorate has an extra oxygen, so that's ClO4 with a -1 charge. Again, notice the charge stays the same, still -1. It's just that instead of 3 oxygens, perchlorate has 4 oxygens. Now, we've already seen the ite suffix, the ite ending. We just drop an oxygen. So instead of ClO3 with a -1 charge that we see in chlorate, chlorite is ClO2 with a -1 charge. Okay, so that 3 drops down to 2, as we saw earlier with examples of, with sulfide, phosphide, nitrite, etc. You just drop an oxygen compared to their 8 versions. Now, you could then drop an extra oxygen, and you would get the corresponding hypochlorite. So you take, if you drop another oxygen from that chlorite ion, you wind up with the hypochlorite version. So instead of having 2 oxygens, we have just 1 oxygen here, but still that -1 charge. If the name hypochlorite sounds familiar, rings a bell, sodium hypochlorite is the active ingredient in bleach. Okay, so if you just take this polyatomic ion and you pair it with a sodium ion, that is the formula of bleach, essentially. So NaClO, or sometimes it's written as NaOCl, that's bleach. Now, that is kind of the toughest part of polyatomic ions, just like recognizing them, and that involves some memorization. All the rules are more or less the same. There's only one extra thing where parentheses come into play. Like, what do we do when we have to put subscripts next to our polyatomic ions? Okay, but in terms of how we balance out charges, how we write out the names of these compounds, all the rules are still the same as we've seen for all of our other ionic compounds. Okay, we're just going to use subscripts if we need more than one of an ion, and using parentheses if we need more than one of our polyatomic ion. And and for naming things, we just say the name of our cation and our anion. It's just that the name of our anion usually ends with ate or ite or something like that. So let's try some practice problems. Magnesium carbonate. Okay, so we're going from a name here into a formula. So magnesium doesn't have a Roman numeral after it, so that should give you a big hint that it's probably in group 1 or group 2. So look for magnesium in your periodic table. Probably found it in group 2, and therefore you see its symbol as Mg. So since it's in group 2, it would form a 2+ ion, Mg2+. Now carbonate, which you can tell is a polyatomic ion from that 8 ending, you kind of have to look it up if you haven't memorized it yet, but carbonate has the formula CO3 with a -2 charge. Now please note that means that there is 1 carbon, 3 oxygens, and this whole thing combined has a 2- charge. Now, the convenient thing here in this example is that 2+ and 2- already balance each other out. They cancel each other out, so you need just one of each ion. Okay. So if you were using the lowest common multiple method, 2 and 2 both go into 2 one time, so that's the lowest common multiple there is 2. If you're using the crossing method, you would you'd realize that your 2's basically, can come down here, but since they're both 2's, you could simplify them to a 1-to-1 ratio. Anyway, the bottom line is that the subscripts here are 1, and which means you don't bother writing them. So we just write out MgCO3. That's the formula. Mg is magnesium, CO3 is carbonate. Okay, like with any other ionic compound, you don't bother writing the charges when you're writing them together in their formula. Okay, now please note the way this is written. You can tell that you have a polyatomic ion because of the multiple non-metals here. Just the fact that you have 3 capital letters tells you that this is not a simple ionic compound with only monoatomic ions, because otherwise there'd be only 2 capital letters, right? One for your metal, one for your non-metal. So the fact that there's 3 capital letters, 2 of them belong to non-metals, tells you that all of these non-metals elements belong together as a polyatomic ion. Okay? And so you have 1 carbon and 3 oxygens, but they are combined into that carbonate. Now, what do we do if we need more than 1 polyatomic ion? So let's look at this example of calcium nitrate. Calcium, like magnesium, is in group 2, so it has the symbol Ca and a 2+ charge. Nitrate, if you haven't memorized it yet, is NO3 with a -1 charge. Now, notice that we have 2 positives here, but only 1 negative here. So just like before, we're going to have to balance this out using either our lowest common multiple method or our crossing method. But you'll quickly find that we need 2 of these negative nitrates to balance out the 2 positive charges on our calcium. So we need to have a subscript of 2 next to our nitrate. So how do we show that? We want to show that the 2 that we're going to write applies to the whole polyatomic ion, not just the oxygens. Also, if we just write a 2 right next to that O3, it gets a little confusing because it looks like you're saying there are 32 oxygens, which would be really weird. So instead, we put the nitrate in parentheses. So you put parentheses around the NO3, and we put that subscript of 2 outside the parentheses to show that the 2 applies to that whole nitrate ion. Okay? And that's how we'd write out the formula of calcium nitrate. Okay, so why don't you try this one out? So pause this video, take a stab at this one. So here you have iron 3 sulfate. Okay, so ask yourself, what's the formula of iron Roman numeral 3? And what's the formula of sulfate, which you may have to look up if you haven't memorized them yet. So here are the symbols of the ions we're using. So Fe has a 3 plus charge and SO4 has a 2 minus charge. So again, ask yourself, how do I balance that 3 plus and 2 minus charge? Using my cross multiplying method, my lowest common multiple method, or my crossing method? Okay, so hopefully you've had a chance to try this out, and you quickly realize you're going to need 2 iron ions and 3 sulfate ions. We balance it the same way we balanced iron 3 oxide. It's the same math, right? Now, again, though, we have to put those subscripts in our formula. So when we do so, to show that we have 2 irons, we put that, as a subscript for iron, which you can do, right? It's a monoatomic, so it's understood that that 2 belongs to the iron. But for our sulfate, since it's a polyatomic ion, you've got to put it in parentheses and put the 3 outside that to show that that 3 applies to your whole sulfate ion. Okay. If you want to try a practice problem involving 2 polyatomic ions, a good example here is ammonium phosphate. So if you look up ammonium, okay, which again hopefully you'll start to memorize as the only positive polyatomic ion you need to worry about, and you look up phosphate. Phosphate is PO4 with 3 minus charge. You can balance these out as normal, right? So how many positives do we need to balance out these 3 negatives? Well, you probably quickly figured out that we need 3 of those ammonium ions for every 1 phosphate. So let's put those subscripts. Well, if we have to put a subscript of 3 for ammonium, to show that it applies to the whole ammonium ion, we have to put our ammonium ion in parentheses before we put the 3 there. Now look at phosphate. There's only 1 phosphate, and notice that because it's a 1, we don't have to write it. Okay, it's understood when you have 1 of an ion that, by not putting a subscript, it's understood that there's 1 of that ion. But also notice that because there's only 1 of the phosphate ion, we do not put parentheses around it. Okay? Please note, the formula phosphate is PO4. There's 1 phosphorus and there's 4 oxygens, but it's still only 1 phosphate ion. I think a common mistake that students make is they look at that and they see, oh, there are 4 phosphates because there's a 4 over there. Again, that's an artifact of how we treat monoatomic ions. And this is why memorizing your polyatomic ions and getting ready to recognize them when you see them will make your job a lot easier. Though, of course, until you get to that point, you can figure that out by just seeing the number of nonmetals making up your compound. All right. When it comes to naming compounds involving polyatomic ions, the names are still the rules are still the same as we saw before. You say the name of your cation, you say the name of your anion. It's just that here your anion has some polyatomic name, right? It's something ending with an 8 or ite usually, and you need to memorize that or look it up. The rules for your cation are still going to be the same. If it's a group 1 or 2 metal, just say the name of the metal. If it's a transition metal, figure out what the Roman numeral is by working backwards and put that Roman numeral in your formula. In your name when you're writing out the name. So let's try some examples out. Here we have CaSO4. Ca is calcium. SO4, with a 2 minus charge, is sulfate. So the name is simply calcium sulfate. We're just combining those calcium ions and those sulfate ions accordingly. Okay, so try naming these ionic compounds. You'll see that when it comes to that metal, again, if you recognize it's in group 1 or 2, or it's aluminium, zinc, or silver, you don't need a Roman numeral in the name, and you just say the name of your cation and the name of your anion. So hopefully it should be relatively straightforward when it comes to naming them. Okay. All right, so hopefully you've taken a stab at those other 2. So you quickly discovered that the second one is just lithium carbonate. Lithium's in group 1, so it doesn't need a Roman numeral. And then you have aluminium nitrate, and of course aluminium doesn't need a Roman numeral either. Like aluminium, zinc, and silver, despite not being in group 1 or 2, since their charges are known, you just call them, you just say aluminium nitrate without a Roman numeral. Okay, so like I said, these rules are pretty much universal for all ionic compounds. So in a nutshell, when you're writing out a formula for an ionic compound, figure out the charges on your ions. What are the positive charges on your cation? what are the negative charges in your anion, make sure that you're trying to get a net charge of 0. So how many do you need of each of those ions to balance out those charges? Then write those numbers as subscripts. Okay? And then, of course, when it comes to naming them, use your, you know, use your the name of the cation and the name of your anion accordingly. All right. For homework for this chapter, there aren't any good end of the chapter problems. So what I recommend here is looking at the example problems in each section of your textbook. Also, be sure to do the compounds and their bonds lab, okay, if you haven't already done so. There are practice problems in each of these types of ionic compounds, so they give you really good practice at each of these. Really, this is a very procedural thing. These are new rules you're learning, so they seem clunky the first time you do them. But once you practice them, and just keep practicing them, they become kind of second nature. It's kind of like learning a language. You're essentially learning how to talk chemistry. When we learn the symbols for the elements or look them up, it's kind of like learning the alphabet. Well, here you're just learning how to take letters and write words with them. That's effectively what you're doing. And just like any elementary student trying to learn how to speak English, here you're a novice student learning chemistry. You're learning how to talk chemistry. You're just going to have to keep on practicing it to get better at it. So if you do ever run out of practice problems, let me know. I can look up some more for you. But I'm just Googling nomenclature worksheets. If you just Google Ionic nomenclature worksheets, I'm sure you can find several practice problem worksheets on the internet, and that will have answer keys that you can use to check your work. All right. But anyway, my point here is definitely practice this stuff. This gets way easier the more you practice it. So yeah, if you have any questions, please let me know, and good luck.